Good morning. This lesson is going to seem like it's kind of not in the right spot, but it is, trust me. We've been doing stuff with radicals. We've done simplifying radicals, simplifying higher order radicals, multiplying radicals, dividing radicals, adding and subtracting radicals. And now all of a sudden I'm hitting you with a lesson called laws of exponents. Doesn't seem like it makes sense, but trust me, it does make sense. There's a reason why this lesson is located here. I'm hoping that I can get this content part of this lesson in about 30 minutes, and then the next class period is just going to be practicing. Before we get into the laws of exponents, I want to make sure that we have a good working definition of what an exponent is. And I actually had to modify this before because students would call me on it. An exponent, okay, tells us how many times something is used as a factor. So how many times something, it could be a number or a variable or some combination, is used as a factor. And of course, factors are things that are multiplied. Factor. So for example, if you see 2 to the 4th power, that means that 2 is used as a factor 4 times. And that is equal to 16, not 8. Okay? 2 to the 4th power. 2 times 2 times 2 times 2 is 16, not 8. And so that's what the exponent is. It has to be written a little bit smaller, and it has to be written as what's called the superscript. It has to be written a little bit above. Now, there are 6 different laws of exponents that we're going to go through. On the next slide here, I'm going to set up a chart for the laws of exponents, and you should probably do the same thing. We're going to use some lined paper, and I have about 9 lines deep and 3 columns wide, assuming that you're not writing with your fingertip. So I'm going to go ahead and set mine up. It'll look something like this. And the first one, and then I'm going to totally ignore my lines. That should be about 1 line. The first 2 can be about 1 line deep. The next one, though, is going to have a fraction in it, so we need to allow a little bit more space to write the fraction. The next one does not have a fraction, so you can go back to like kind of normal. And the bottom 2 are both going to have fractions, so you just need to make sure that you're allowing enough space. The column on the left can be fairly narrow. Soak in the column in the middle. I don't know why I have that so wide. And then the column on the right, you want to be your widest. That's going to be the column where we put the example. Now, what I want to do is I don't want to just hit you with 6 laws and expect you to memorize them and be able to use them and have them make sense. That's not super realistic that you can see something once and just have it click. You should have seen most of these before. Or at least like 2 or 3 of them. If it were up to me, you would have only seen 3 of them. So 3 of them would be old, 3 of them would be new, but the old ones you know really well. And I kind of think none of them are new, but you might not know them very well. So as we go through this, I'm going to click over to the slides on like the next few slides and work out some reasoning and some thought process. If you're looking at the scanned copies of the notes, you'll see that there's like a whole chunk that just says the reasoning. Why does this law work the way that it does? And that is so important that the laws make sense to you. So for this first one, this is what we call multiplying like bases. So that is x to the a times x to the b. Just for some vocab, okay? This is called the base. It's whatever is being raised to the exponent, and then you have the exponent up there. Okay, so when I say multiplying like bases, I am referring to the fact that these are both x's. So like bases means they're both x's. If they're not like bases, you're actually not going to do any multiplying. So if you have x to the a times x to the b, that can be done by adding the exponents. So x to the a plus b. And now that you see that, it might seem familiar. Hopefully somebody in Algebra 1 at some point introduced you to that. Now the question that you might have though is why? Why do you add exponents? Not just because some teacher somewhere said, hey, add the exponents. It should make sense. So what I'm going to do is work out kind of an illustration or an example for you so that you can see why adding the exponents is a logical thing to do. Suppose we had x to the third times x to the fourth. Now, using the definition of what an exponent is, this is x times x times x. And the one on the right is x times x times x times x. And what's happening in between x to the third and x to the fourth? That would be multiplication. And so what we have here is x times x times x times x times x times x times x, which would be x to the seventh. X used as a factor 7 times. Note that it would be quicker if you just did 3 plus 4 to get the 7. But that's why you add the exponents. When I taught, and we'll put that over here, like if in our chart, if we have x to the third, that was kind of bad, x to the third times x to the fourth, that is equal to x to the seventh. When I taught Algebra 1, what I would do with my students is I would give them a whole ton of problems like that. And usually by the time they got to like the third problem, they would figure out that it would be a lot faster to do that if you just added the exponents together. And so I would try to let my students actually discover the rule on their own rather than me just telling them, oh, here, this is when you add exponents. Now, the cool thing about this is if you forget what the rules are, you can go back and just a couple of years ago, I came up with that when in doubt, expand it out. So if you forget whether you're supposed to add the exponents or multiply the exponents, you can always fall back on this where you would just expand out the expressions and you can figure out what the rule is. All right, let's look at the next one. This one is called the power rule. I don't really care so much about whether you know the names of the rules. But this would be like if you take x to the a and you raise that to another exponent. So you have something that's raised to an exponent and then you take that whole thing and raise it to the exponent again. When you have that, you multiply the exponents. So everything is all happy until you start having to keep these straight. Like, when do I add exponents? When do I multiply exponents? Well, you know what would be great is if that made sense to you. So let's pick, let's do x squared raised to the third power. So I went back, to the definition of an exponent. It tells us how many times something is used as a factor, because you need that definition if you're going to pull this apart. This tells me that this expression is used as a factor 3 times. So x squared is multiplied in 3 times. In other words, it's x squared times x squared times x squared. That's what the raising it to the third power means. Now it actually looks like this, where now you're multiplying something. But if you still blank out, you can still do this. X times x times x times x times x times x. And lo and behold, you have 1, 2, 3, 4, 5, 6 x's there. So that is x to the sixth. A quicker way of doing that would have been to do 2 times 3. And again, if you forget the rule and you're like, I don't know if I'm supposed to add these, I don't know if I'm supposed to multiply them, it happens, then you can always expand it out as long as you understand the definition of what an exponent is. It'll take you a little bit more time, but you'll get to the right answer. And after you do it like a few times, you won't have to keep doing it out. So this is our example. X squared raised to the third power is equal to x to the sixth. All right, next one. This is one that I actually never use except on the day when I'm teaching it because I don't like it. And if you understand math well enough, you can avoid the stuff you don't like because you can figure out ways around it. So this is dividing like bases, where you have division. And again, like bases means that you're dealing with a base of x in both. And this rule looks something like this. You subtract the exponents. You always subtract the denominator exponent from the numerator exponent, and you always have to subtract in that direction. It's always subtracting the denominator exponent from the numerator exponent. Notice that I'm saying exponents, because there is a weird mistake that students start to fall into. So why does this make sense? Like, we want our rules to make sense to us. So let's look at this. What if you had x to the fifth over x to the third? Well, let's engage the definition of an exponent. It tells you how many times it's used as a factor. So this is x multiplied by itself there. And we have 5 x's, and then we have 3 x's. Now, keep in mind, 2 divided by 2 is 1. Negative 4 divided by negative 4 is 1. 1.2 divided by 1.2 is 1. Therefore, some unknown number x over itself is 1. And that's why the x's cancel out. Don't let people just tell you, oh, they just clearly cancel out. If you don't know why something cancels, ask, why does it cancel out? It's an excellent question, and I'll probably tell you every time. That was an excellent question. So we've got all these x's over x's that are equal to 1. And they do cancel out because they're equal to 1. And what am I left with? X times x, which is x squared. What would have been maybe easier is to just do 5 minus 3 to get the 2. And so you could have gotten the 2 a quicker way other than expanding it out. I'm actually a pretty big advocate of expanding it out on these ones. I told you I didn't like this rule. So, all right. So we have, what was our example? X to the fifth divided by x to the third, and you get x squared. So now we get into some of the weirder rules that you might not know and might be counterintuitive, but they're kind of fun too. So x to the 0. That's a 0. There we go. Your intuition, and by intuition, I mean your gut instinct, like that thing that pops into your head right at the moment when I say x to the 0, is probably 0. Because you're probably thinking, well, if the exponent tells us how many times something is used as a factor, and it's used as a factor 0 times, then I probably have nothing there. It should be 0. And that's actually not a bad thought process. It's going back to the definition. But it doesn't work here. So the actual answer to this is 1. And immediately, if that's not something you've had explained to you, you should immediately think, why is it 1? Because we know math is consistent and we know math makes sense. And so if it's 1, there's a reason, like a really good logical reason for why it's equal to 1. So we're going to work this out by looking at the same problem 2 different ways. We're going to look at x to the third over x to the third. Okay? Now, I know that anything divided by itself is equal to 1. Okay? Now, if you wanted to, you could go through this, and then you could see that all of your individual x pairs all cancel out. But we know that anything divided by itself is 1. Like, that is an established mathematical fact that you guys have encountered since 3rd or 4th grade. But we also know that when you divide like bases, you can subtract the exponents. So this would be 3 minus 3. And 3 minus 3 is 0. If I know that this is rock solid reasoning, and this is rock solid reasoning, then the only logical conclusion I can draw is that x to the 0 has to be the same as 1. Just has to be. Now, for your chart over here that I hope you're writing down, I actually have in here like a numerical example, like 3 to the 0 is equal to 1. If you don't believe me that 3 to the 0 is equal to 1, go grab your calculator. Go do it right now, okay? We'll stall for a second here. So you can grab your calculator and put in 3 to the 0. I promise you, your calculator will tell you that it's equal to 1. Okay? It will. It gets weird. It gets weirder. It's about to get weirder. You ready for it to get weirder? I hope so. So now we get to the negative exponents. Okay? And now it just feels like our definition of exponent just got blown out of the water. If an exponent tells you how many times something is used as a factor, how can it be used as a factor a negative amount of times? And if you're thinking that, then you are dead on right. Like the definition of what we think of an exponent meaning does kind of fall apart right there. You can't have something as a factor a negative number of times, but it means something. Here's what it means. If you have x to the negative a, that is equal to 1 over x to the a. In other words, you are dealing with a reciprocal. And of course, we do not content ourselves with the teacher just saying, oh, okay, it's a reciprocal. And if you've had teachers in the past that have just told you that and expected you to accept it and move on, that is not me. Where does it come from? Why does that make sense? So here we go. We're going to do the same thing we did in the last example. We're going to look at two problems, and we're going to look at those two problems, one problem two different ways, both of which are going to be solid. So if I do something I know is correct and I do something I know is correct, then whatever I get at the end has to be equal. So here's the first thing that I'm going to do. I'm going to expand out x to the third, and I'm going to expand out x to the fifth. And I'm going to do a little something weird here. Would you agree that I can put a times 1 in the numerator? I'll let you kind of think through that. I could just put times 1. Right. Hopefully you thought about it and you're like, yeah, I don't know why you're doing times 1, but sure, you can multiply by 1. Very first lesson of the year, I'm harping on 1 is the multiplicative identity. Anything times 1 is itself. So you can put in a times 1 anywhere you want. Okay, not going to change it. Might seem weird why I'm doing it, but you just got to trust me like you can. Now, I know from my previous reasoning that a bunch of those x's cancel out. And what I'm left with is 1 in the numerator, and in my denominator, I am left with x squared. Now, if I don't kind of put in that times 1, students will tell me that there's a 0 in the numerator, or they'll be confused as to where the 1 comes from after I'm done with the problem. They're like, where'd you get a 1 from? And so I like to kind of establish that and give you a chance to think about it before I launch onward. Now, I am confident that this is good, solid reasoning, that all of these things cancel out, that I am able to put the times 1 in there. So x to the third over x to the fifth does equal 1 over x squared. I also know, because of very solid reasoning, that I can subtract those exponents. And you always subtract the denominator from the numerator. So it's going to be 3 minus 5. And 3 minus 5 is negative 2. That's where your negative exponents come from. If I have good reasoning here and good reasoning here, then I have nothing left to conclude other than x to the negative 2 has to be equal to 1 over x squared. And that is the only logical conclusion. Now, I know I only did that with an exponent of 2, but you could tweak whatever problem you want to start with, and you could do it for 3, 4, 5. You could do it for whatever you want and eventually come up with the same answer. So clicking back over here, the example that I have there, we'll put a couple of examples in here. We'll do x to the negative 2 is equal to 1 over x squared. I also have 2 to the negative 2 is equal to 1 over 2 squared, which is, let me clean this up a little bit. I'm trying not to erase the word reciprocal there, but I just don't have space. 2 to the negative 2, which a lot of people would say is negative 4, but it's not. It means 1 over 2 squared, which would be 1/4. So it means the reciprocal of it. Now, the last one that I have here, and I'm like running out of colors, is 1 over x to the negative a. So what if the negative exponent is already in the denominator? Like, now what? Like, what do we do if it's already in the denominator? So follow along with this. This is going to be a little bit rocky, but like I promise you, you'll be okay. So if you have 1 over x to the negative a, we know that x to the negative a is 1 over x to the a. Now that right there is actually, it looks terrible, but it's not. It's called a compound or complex fraction, and it's when you have a fraction inside a fraction. So the denominator of the fraction is a fraction. They look awful. They look like they're the scariest thing ever, but they're actually not that bad. They actually aren't. Now, here I'm going to pull a little vocab trick here. A fraction bar is nothing more than a division symbol. So instead of writing this as a fraction, I could write it as division. Like 1/2 is the same as 1 divided by 2. I'm going to do this and write it as 1 divided by 1 over x to the a. And all I did there was a slick little notational change where I subbed out one division symbol for another. Now the definition of division is multiplication by the reciprocal. Way back, first lesson of the year, I said there's no such thing as division. Division is just multiplication by the reciprocal. So instead of writing division, I can write multiplication, and I'm going to take the reciprocal. So that would give me x to the a over 1. But what's x to the a over 1? That's just x to the a. And times 1 is just x to the a. So this 1 over x to the negative a is just an awful way of writing x to the a. Oh man, I am like way far. Okay, and as an example over here, I have, if you had like 1 over 4 to the negative 2, that would be equal to 4 squared or 16. Now, in summary, your negative exponents, all they really mean is that you deal with reciprocals. If you have a negative exponent in the numerator, you can write it in the denominator as a positive exponent. If you have a negative exponent in the denominator, you can write it in the numerator as a positive exponent. Once you can kind of get your head around that, life is so much easier. I've got about 7 minutes left and before the video kicks me out, and I have 3 example problems that I'd like to get through before, okay, I've got like this done in like different colors here, before the time is up, and then that will free us up to spend the whole next class period just on practice. Now, where people start to kind of fall apart with this is now you've got like multiple things going on. So you might have like multiplication of exponents or addition of exponents and so forth. When you're dealing with something like this where you have multiple things in the parentheses and then the exponent is on the outside, it means everything in those parentheses is raised to that exponent. So there's 2 ways you can tackle this. I'll actually do it both ways. I'm going to risk running out of time here, but the way that I would probably do this is I would remember that raising a power to a power means you multiply exponents. And you need to remember that the exponent on the 2 is a 1. That's 2 to the first power, and this would be 1 to the first power. So you would do 2 to the 1 times 4, which would be 2 to the 4th. Then you do x squared, and you're going to multiply those exponents. So 2 times 4 is 8. And then on your y, 1 times 4 is 4. And then probably you would take the 2 to the 4th and write it as a 16. Some of the students will say, well, can you leave it as 2 to the 4th? Yes, technically. Usually, if the number is less than 1,000, I would do it out and write it, as long as it's like 3 digits. If it gets like really big, like it's like 20 million, like no, like leave it as an exponent. Now, let's just say you forgot what you were supposed to do. When in doubt, expand it out. Kick it back to the definition. So raising something to the 4th power means that you would multiply it by itself with it as a factor 4 times. So you're going to have this thing 4 times. Now you just can see it differently. Now you can see, oh, it's 2 times 2 times 2 times 2, which is 16. X squared times x squared times x squared times x squared. That's 1, 2, 3, 4, 5, 6, 7, 8 x's. And you've got y times y times y times y, which is y to the 4th. Is this a little bit longer? Yep. But does it work? Yes, it also works. Let's look at the second example. This is 4x to the 3rd, y to the 5th, over 2x, y to the 7th. What was I doing there? Now, for this problem, I actually like to use a visual technique where I split this problem into 3 separate problems that I think are easier to deal with. And so this is what I do. I miraculously shrink my problem down so I have more space. But I actually do this. I split it up into 4 over 2, x to the 3rd over x, and y to the 5th over y to the 7th. I did not actually do any algebra. All I did was put a little bit of visual space in between the sections to help my brain process what I'm looking at. Most of you won't need to do that. You'll be able to process it separately even when it's written together. And now take each part separately. So 4 divided by 2 is 2. Over here, we'll do a little bit of scratch work. I don't ever use, I mentioned earlier, I don't ever subtract exponents, or I very rarely subtract exponents. I always think of it this way. I have 3 x's in the numerator, 1 x in the denominator, something cancels. What am I left with? I'm left with 2 x's, and where are those x's? They're in the numerator. And then I do the same with the y's. So I'm like, okay, I've got 5 y's in the numerator. I've got 7 y's in the denominator. 1, 2, 3, 4, 5, 6, 7. And I don't write it out. I'm writing it out for you guys. I would say, okay, some of them are going to cancel out. What do I have left over after they cancel out? And you guys would say, you have 2. And I would say, where are they? And you would say, they are in the denominator. And there you go. This I usually just talk through. So when we're doing them in class, I'm probably going to just talk you through them. I'm not going to write, but that's what I would do. And you could really go from this first line straight down to the answer without doing any work. That would be totally reasonable. Last problem is this one, and it is y to the negative 3rd to the 4th all over y to the negative 5th. And there are so many different ways you could do this. So if I've got time, or if I've got about 2.5 minutes, I'll see if I can do it more than one way. I don't know. That's like ambitious. So the way I did this in my notes was I recognized that I'm going to multiply these exponents together. So negative 3 times 4 is negative 12. Then you've got some options. I like to use the reciprocal option. So a negative exponent in the numerator, I can write that in the denominator as a positive exponent. And a negative exponent in the denominator, I can write as a positive exponent in the numerator. So this is y to the 5th over y to the 12th. And then I'll actually just talk it through. If I have 5 y's in the numerator and 12 y's in the denominator, so you can picture them, just kind of picture them all out. I'm going to cancel a bunch out. How many do I have left over after I've canceled? I have 7 extra y's. And where are the extra y's? The extra y's are in the denominator. And what am I left with in the numerator? Just a 1. You can also do that one. Let me see if I can. So we got this, and then we had this. So I don't know a great way other than you got to multiply that first. But some of you are going to do this. You're going to say, okay, I subtract exponents. So negative 12 minus negative 5. Be careful. You're subtracting a negative, which means that you're adding. Well, negative 12 plus 5 is, I don't know what I'm doing. I'm panicking because I'm watching the clock, is negative 7. And then a negative exponent means a reciprocal. So you end up in the same spot. And I think you kind of see why I avoid subtracting exponents, because who wants to do that? One of the things I love about these kinds of problems, though, is that there's not just one way to do them out. There's often multiple ways and multiple places to start. So I know that was kind of rushed through the examples. You guys know the videos on YouTube if you want to rewatch the examples. And we will take tomorrow to do our practice.